Hello everyone, I hope you are all fine. Our purpose is to define a parameter and derive the expression for it. The parameter would be important because it gives us the properties about subatomic world. Our macroscopic world is visible to our naked eyes, but we can't see what's inside this chalk, means what is the microscopic world look like. For that, we don't have any microscope which will amplify or zoom the object. We basically do scattering. Through scattering, what is the output of that scattering? We study the scattering particles and get some information about the target or the specimen we have scattered the specimen. For example, in electron microscope, what you I think you would for example, in electron microscope, it is not like that we zoom in something object. In electron microscope, it is not like that. That is, our phone camera is. In electron microscope, it is not like our phone camera, that is zooming a object further and further. Electron microscope works on the principle of scattering. Let's say it's an object, we want to study this. For that, if you use electron microscope, what is done by the electron microscope is it sends a beam of electron to the specimen you want to study. After that, the beam of electrons are scattered by the specimen, and those scattered electrons, or I can say this could be, say, a current density of incident electrons, and this could be visualized or named by the scattered current density of electrons. And if you study these electrons, we can predict what is the cause of this scattering. By this scattering, we conclude what is this object. And that's how we can know the properties about any microscopic world, objects. Basically, if you change the specimen and change the observer or the object, basically if you change the specimen and the your device, here it comes electrons, and if you change it to protons, to neutrons, and further particle, by changing these incident particles and the specimen, you are able to know what is microscopic world look like. And for that, a simple parameter called scattering parameter is very important. What is it? Let's say it's a target or a specimen. I am magnifying it to visualize it properly. What happens is, when a incident beam is strike the specimen, it strikes only some area of the specimen, and let's say it is the area that is influenced by this incident beam or incident current density. Let's denote it by JINC. And this incident beam, what is meant by beam? Let's discuss it first. If you are throwing just one particle, let's say I am throwing one chalk, so this would be throwing one chalk, and if you collect a bunch of chalks and throw it once, then we can say it's coming a beam of chalk particles. Like that, if you throw some microscopic matter or microscopic particles with bunch of those simultaneously and with high energy, then we say it's a beam of that microscopic particle, right? And what happens after this collision? We say it collision, the beam would be reflected like this, It's clear. If I throw the chalk to the board, the chalk would be scattered in some angle, in some way. Let's see. I am throwing this chalk to the board to illustrate to you. I can throw these two chalks for the sake of physics. Let's throw it. What happens? The chalks further breaks. Chalks are spread out through the entire area of this board, and that's how, in this case, as the particles are coming in such a high energy, the particles will be scattered in this angle with some making some solid angle, means it will be scattered in this area, and further there will be some particles, but we neglect those particles. And of course, for neglecting those, we have to choose a frame of reference, and we say this is our axis, and from this axis this scattered ray or beam is making an angle theta and phi, and we will define a parameter, a correction parameter, f of theta and phi, which will resolve the error, resolve the error that would be arise due to further scattering of particles. Means after scattering, if it's a target, it's a point, and what is our beam? Beam is a parallel beam, because from the target our source of uh, incident particles is far away. We can say the incident particles are coming like a waveform, a plane waveform, and after scattering this wave to this target, it will create spherical waves. So whenever this incident plane wave reach this area, there will be a spherical wave seen by our detector, because our detector is throughout the target, not like this. Not this is just an example. A small portion of our detector is here shown, but actually the detector would be covered the total target or specimen. In such a way, there will be created a spherical wave front or wave by the incident beam, and by detecting this scattered beam, we will further make the conclusions about the target. For that, we have to choose at first a small area. From a small area, what happens? There will be scattered beam through some solid angle. If you cut a sphere's small portion, it makes a solid angle. It's clear for everyone. So let's denote this solid angle by d omega. And what is the area? That the area means the surface. If consider my hand as a area of a football. In that case, the area of this palm is not same as the solid angle. Solid angle is this. This is the angle by which something is created. If you consider this, the book, using this book, we can create a solid angle. So this is the solid angle. The angle you are seeing here, it's called angle, and we denote this angle by d omega. And the upper surface, if you cover this, and if you cover this portion, if you cover this front portion with some papers, the area of that paper would be the area of that solid angle. So this is the area. This is the area, and we denote this area by dA. And what is the relation between this solid angle area and solid angle? This area is denoted by, this is the distance r square multiplied by d omega. So this is the relation between solid angle and the area. Further, we have done with everything, and just we have to define the parameter called differential cross section parameter. So in this small area, the scattered particles will be scattered in that way, making an angle theta and phi, and these scattered particles are called, and the parameter we are going to talk about is the differential cross section. So this is the small cross section, we are denoting it by d sigma. This is the parameter we are going to calculate. We are not calculating the d sigma only, we have divided it by d omega. The purpose of dividing d omega is to quantify this to a specific solid angle. When you want the whole cross section, you just have to integrate it. If you integrate it by multiplying d omega here, you will get the total cross section sigma t. So d sigma is just a small cross section called differential cross section, and what it denotes? It denotes means its definition is d sigma by d omega is equals to 1 by incident current density JINC, and this is this incident beam's current density. First you have to divide it by that, and we have to multiply n theta phi divided by d omega. What is d n theta d phi? The number of particles in this solid angle. So number of particles coming per unit time. Inside this solid angle there are many particles, and we define n per unit time. If you consider number of particles in this solid angle, that would be n theta comma phi, and if you divide it by this solid angle, we will get differential cross section by d omega. So this is the term we are going to derive, and this would be equals to, means this d sigma by d omega would be equals to incident